Swayam Prabha. Digital India. Educated India.
Okay, so let me first summarize what we have discussed so far in this module. So basically, we realized that prescription of the carrier phase a priori is not possible always. So this means that we have to solve the governing equations for the particles as well as the carrier phase together, and this poses formidable challenges, especially when we try to resolve the flow, which means that we resolve the flow at the particle scale, which means that we we resolve the flow around individual particles, capturing the boundary layer for each particles. So that is quite challenging, basically computationally expensive. So that is why we rely on volume averaging. So which means that the governing equations must be integrated about a volume, or considering a grid of certain volume, and the governing equations are written for that volume. So in such case, what happens is that we have source terms appearing in the mass, momentum and energy equations. So these source terms are basically those terms which couple the two phases, which basically represents the fluid particle interaction. Okay. So and we have seen this for mass, momentum and energy equations. However, at this point, it is very important to note that these equations, for example, let's say momentum equation, this momentum equation cannot be considered as Navier-Stokes equation plus a source term. You may wonder, why not? So if you see the form of this equation, this is Navier-Stokes equation plus this source term. However, it is not correct to interpret it this way, because this flow parameters that we observe here, for example, the flow velocity, it is not defined at a point. This is volume averaged over a grid volume. Similarly, pressure. While in case of Navier-Stokes equation, we have a partial differential equation, and that equation is valid at every point in the flow. However, this is not the case here. So we are averaging the flow parameters. So we have to keep that in mind. Then, to simplify the coupling terms, we introduced an assumption called point particle assumptions. So in this case, the particles are treated as points. So we account for their interaction effect. For example, drag, heat transfer, we account for that. But the particles as such don't occupy finite volume in space. This means that the particle as such don't disturb, or they cannot disturb the flow. For example, vortex shading or particle interaction also. Okay. So there is no as such direct particle interaction that is possible in this case. Okay. So the condition, so under what condition we can do? That is possible when the particle diameter is smaller than the smallest length scale of the flow. The particles have to be very small. First condition. Second condition is that the volume loading or the particle mass loading is quite small, such that we have quite low, such that we have dilute regime. So the consequence of that is you don't have particle-particle interaction, or the probability of particle collision is negligible. Now, the main advantage of that is, here this is computationally efficient. So, that is the main objective of this particular point particle assumption, and it is applicable to a large number of particles. And in this case, we have basically Euler-Lagrange framework, which means that we are treating the continuous phase or the carrier phase in the Eulerian reference frame, but the particles in Lagrangian reference frame. So, this is called Euler-Lagrangian framework. But the limitations are basically it fails when the particle size is comparable to or larger than the float scales. So, for large particles, we may do this simulation, but it is not realistic, because we won't be considering the effects due to the disturbance created by the particle in the flow. So, we cannot resolve, for example, wake formation, and it is obviously less accurate when we have dense regions where particle-particle interactions become prominent. So, these are the governing equations for the carrier phase. These are all volume averaged governing equations which we need to solve. And if you see here, in these cases, because of the point particle assumption, we have brought in some simplifications. For example, here we are considering only Stokes drag mainly, and here we are considering the heat transfer, the convective heat transfer effect. Plus, we can also account for the heat transfer due to mass transfer. All those are possible, but here we have neglected particle collision, vortex shading, added mass, history effects. So, this means that again this is valid when we have dispersed phase density much larger than the carrier phase flow. For example, droplets in air or dust particles in air, but it won't be applicable for bubbly flows. It will be, it may be even in that case if the bubble size is very small, which are not deforming. Let us say you have micro bubbles which don't deform in some application, then you may consider this. Okay. So, now moving forward, now we know that even if this point particle assumption is useful in the sense the computational cost reduces, we know that, but still in real world applications we have millions to billions of particles in the flow. Now, tracking each and every particle is definitely computationally expensive, and it may be impossible also many times. So, even after we have the point particle assumption, because anyway you have to track those number of particles. So, that is why people have come up with this type of modeling. It is known as discrete parcel method, or DPM. You might have heard of this. This is quite popular in the simulation of dispersed multiphase flows. So, basically this is a computational shortcut. So, this means this is not physically realistic. Okay, this model is brought in to reduce the computational time, as simple as that. So, here also we use the point particle assumptions, but instead of particles we define something called parcel. Okay. So, what is a parcel? Parcel means here we have a group of particles which have same size, same velocity, same temperature, same composition. So, for instance, you have collection of, so these are the parcels that you track. You don't track particles but parcels, and in each parcel you have many particles, such that in a particular parcel, the characteristics of all particles are same. For example, this may have, let's say, 10,000 particles with 10 micron diameter, and this may have, let's say, 10,000 particles with 21 micron diameter. So the particle size is different. Maybe the temperature is also different, composition are different, but everything is same within one parcel, and you track the individual parcels. So in this case, what would be the governing equations for the parcels? Will it be same as the particles? The answer is yes. So if you see, virtually even each parcel does not have any volume, physical volume or mass, because it consists of particles which are points we have assumed. So all the parcels, basically for all the parcels, the governing equations are same as what we discussed. But then what is the difference is that the source terms feedback to the fluid are scaled by the number of particles in the parcel. So for example, let's say here you want to calculate the total drag term. So now in your grid, you have, let's say, 2 parcels. Okay. So in each you have, let's say, 1,000 particles. The particle size might be different. As I just said, let's say this is 10 micron and this is, let's say this is 100 micron. Now to calculate the total drag, you have to calculate the drag which is basically this part. So this part basically times the number of particles here plus this drag times the number of particles here. So basically the effect is scaled up with the number of particles you have assumed in each parcel. Okay. So finally you have to account for the effect due to all particles but in different parcels. So that is the way we handle it. So what is the advantage? Advantage is that you are still solving for number of you are still solving equations for the same number of parcels. So let's say here you have 5 parcels. But how many droplets you have? If in each one, if you have 1,000, then actually this is 5,000. So you are considering 5,000 particles but 5 parcels. So this is the reason why the computational cost goes down, is drastically reduced. However, obviously the accuracy depends on how well the parcels represents the statistical distribution of particles. Okay. So rigorous validation with experiments is essential to establish that whatever results, whatever predictions you are getting from this is valid. Okay. And it is used in the applications where we have dilute loading. For example, if you are considering a spray, then if you should not consider the near nozzle locations where the particle number density is high and particle-particle collision is possible. Also in that region, two-way coupling might also be possible. Okay, two-way coupling you can handle using point particle method, but still it is not suitable for that region. So if you model that region some way and release your particles, then in the dilute region you can track. For example, let's say you want to look at the spray structure, then you have to inject the particles with suitable size and velocity distribution after certain location. from the exit of the injector. Okay. Or else you can also release the particles from the exit of the injector, but the near nozzle results are not realistic. Okay. So this is discrete parcel method, which is based on point particle assumption. There is another approach which is known as discrete element method. So discrete element method is basically similar to DPM or discrete partial method, in the sense that here also we are referring to Eulerian Lagrangian multiphase flow framework. Like in case of DPM, here also you have. But in the case of DEM, we don't have parcels, we have particles only. Okay. So obviously this is computationally expensive. Now in this case also, we model the interface exchange terms, for example, drag, lift, heat, mass transfer, etc., as in the case of point particle. So from that respect, the particles are point particles. And here also we have the source terms in the Eulerian fluid equations and our model similar to DPM. However, in case of DPM, the particle collision is usually neglected because, as I said, the volume loading is low. There are some approaches which consider DPM but particle collision also to account for, to basically simulate, for example, near nozzle locations. How do they do that? Is by modeling the collision stochastically. So it is not like they can have real collision between particles, but they consider probability of collision between particles, similar to kinetic theory of gases. We have considered a model, if you remember, to calculate the collision frequency, if you remember, sometime earlier. So it is something similar to that. So in this case, we prescribe a probability of particle collision based on the relative velocity between particles. However, that is not physical, it's a kind of a model only. So accuracy of that model is questionable. For example, the number of collisions may increase if you increase the grid size, because it considers the number of particles in a grid. So if you have higher number of particles, you have higher number of collision. So the result would change significantly if you just change your grid size, which is not correct. Okay, so those kind of problems we may encounter if we try to include particle collision in DPM. But in case of DEM, the particle collision is explicitly resolved with contact mechanics. So from this perspective, the particles have finite volume and shape. Okay. So if you see, as far as modeling the interface exchange is concerned, this is point particle. But as far as modeling collision is concerned, this is physical particle. So this is the main difference basically. So now if we compare the particle number counts that the DPM and DEM model can handle. So if you see, in case of DPM, we have relatively lower number of particle count, and that is 10 to the power of 5 to 10 to the power of 6 parcels. While in DEM, this is 10 to the power of 6 to 10 to the power of 7 particles. So you should look at this. So here we have parcels. This is particles. So if you calculate the number of particles, it will be used in case of DPM. So DEM is possible with this kind of particles, but obviously it is much costlier than DPM. And where do we use the discrete element method? Where basically the particle-particle interactions are important. So for example, powder handling, fluidized beds, slurry transport. So in those cases where we have high particle loading. Okay. Next, so there is also an entirely different approach to model particle-laden flows. This is called two fluid model. So what is meant by two fluid? We know that we have one fluid, the carrier phase, the other one is particle phase. But in this case, the particle phase is also treated as a fluid phase. You may wonder how that makes sense. But it does, especially when you have high particle loading. So the governing equations must be written for the particle phase accordingly, similar to how you have derived the governing equations for the carrier phase. So this is Eulerian, that is why it is Eulerian approach. So in this case, instead of tracking each particles, both the particles are treated as interpenetrating continua. This means that in your grid, you have now imagine two fluids present together which are interpenetrating, and they are described by the respective volume fraction. And we know that there, we can generalize this, and this has to be 1. So in this case, we need to describe the dispersed phase with its own set of now volume averaged conservation equation. So till now we were considering the equations for the particles from Lagrangian reference frame, but now we have to consider it from Eulerian reference frame. And we can handle the interaction between the phases via the source terms, as you will see. So again, if we consider a generic particle-laden flow like this, then we can try to derive the continuity equation. Again, the approach is same as we did in case of continuous phase. So in this case, the rate of particle mass accumulation plus net efflux of mass must be equal to 0 as per mass conservation. So for 1D flow, again we can follow a similar approach. Okay. Now you see that in this case, this term is minus here. If you compare it with the equation that we used for the continuous phase, it was plus. If you consider evaporation. So if particles are evaporating, particles are losing mass. So that is why this is negative. And here you see that the source term is just negative of what we used for the continuity phase. Okay. And here, instead of the particle carrier phase density, bulk density and carrier phase volume fraction, we have the respective quantities for the particles. But there are differences that we should always note. That is the definition of velocity. Now, what is velocity in this case where the particles are being treated as fluid? This velocity is defined at the center of the grid, let's say, and that is actually mass averaged velocity. So this velocity that you would calculate is not the velocity of a particle, but it is mass averaged velocity. So if you have a polydispersed distribution and if it is polykinetic as well, which means that the particles have different velocity also, then you will have a problem here. So when you do this mass based averaging, so typically we have particle size distribution which appears this way. So you have less number of large particles, okay, but if you calculate the mass probability or volume probability, it is actually like this. If you remember, I had shown this to you. So this means that the averaged velocity will be biased towards large particles because you have the d cube term present here inherently. Okay. So, so this should be mass only, not rate of mass. Okay. So this is one thing. And next thing is that in this case, we don't have particle tracks. You cannot track a particle. So the source term must be represented in terms of the volume fraction rather than the particle size. So if you compare this with the DPM approach, let's say, then how do you calculate this term for a grid? You use d square law model and you have the expression for the mass transfer rate. You just add them up. But in this case, you cannot do that because you don't have individual particles. What you know is the particle volume fraction. So the model must include this expression in terms of the volume fraction. So that is a main change, major change. So just if you add this term now, so the continuity equation for particle phase and for the carrier phase, you will just get 0 because this is negative of the source term for the continuity equation. Okay. Now, similarly, we can derive the other equations. However, we have to be careful. Why? I will show you now. So, this is the momentum equation that is derived in a similar way. So, you see that the form is basically very much similar to what we have for the continuity equation, the volume averaged continuity equation. Here also a source term appears. So, this source term is basically, in this case, the sum of the drag term due to each individual particles and the momentum due to mass transfer in each particle. But this also we have to express in terms of the volume fraction. However, the main point here is that why should you have a pressure here? Like in the case of fluids, why should you have a pressure term? And similarly, what is meant by this stress tensor here? How do you define viscosity for the particles? Does it make sense? So, the answer is, if you have low loading, if your loading is low, then both these terms will be neglected. We can neglect both these terms, they don't make any sense. However, if the loading is high, for example, particles in a fluidized bed where the loading is high, in that case, the particles exchange momentum through collisions. And and here we have a scenario where the velocity fluctuations resemble a pressure plus viscous like stresses. So because of collision, so you have to account for collision, right? And it is possible that we model the collision in such a way that we have a pressure term and a viscous term. So basically we have granular force. Okay. So and accordingly we can define a viscosity. But these are not again viscosities as in the case of a fluid. Okay. Though not shown here, we can derive the energy equation also similar way. Now, again the typical applications, the applications are mainly in fluidized beds, pneumatic conveying. So basically wherever we have usually high loading. Now the main advantage of Euler-in method is that here we know we don't have to track each particle or droplet. Okay. So the basically it is computationally cost effective, especially when you have like particles in say fluidized beds. There tracking individual particles does not make much sense. Okay. So and it is suitable for dense flows where point particle methods are not feasible. But the limitations is that you cannot track individual particles. Okay, so here we have less detailed information and we get only the averaged field. For example, here what would you get is what is the volume fraction. But if you see in such applications where this is suitable, there tracking individual particle is not important. What is important is actually the volume fraction. For example, you take a fluidized bed. You have particles initially which are at rest. You start the airflow or the gas flow. Then the particles would try to suspend. However, this phenomena is not as simple as I am talking, because in this case the particle volume fraction is not uniform. What happens? Large bubbles appear in the bed. So bubbles means you don't have particles here, you have particles all around. So in such cases, we want to know how is the distribution of the volume fraction, because eventually this will affect the heat and mass transfer for whatever process you are using it. Okay. For example, coal combustion. So there, this will influence the combustion process greatly and also the pollutant emission process. So here also we need closer models for drag, lift, heat and mass transfer, as I just mentioned. But here the numerical stability can be an issue when we have volume fractions approaching 0 or 1. So we have to avoid these limits. So if the volume fraction is too low, we have a problem in the numerically solving the equations. Okay, so finally, this is another interesting method. This is known as population balance method. So this is a framework basically to capture polydispersity, or when we have distribution of particle sizes in dispersed multiphase flows. So if you want to understand the behavior of individual particles with different sizes, then which approach we need to follow? We can use DPM model, but that is restricted for low loading only. But what if you have high load? Next one is DEM. You can do DEM, but that is also computationally challenging. Of course, the particle number limit is higher than the DPM, but still it may not handle situations like fluidized beds. Then what do you do? So this is a method to account for the polydispersity. So for example, this is the population balance equation. So if you see, this equation is quite similar to the continuity equation for the dispersed phase in two fluid model that I had shown. So just if you see this one. Okay. So here if you consider that the volume fraction is nothing but number density times the volume of individual particles. So if you write in that term, it is possible to show that finally this is a function of the particle number density. So basically here you have an equation for particle number density. Okay. Now this number density is not only function of space and time, but also particle size. And here we have basically the source term, you can say. For example, this represents the growth rate. Let's say the particle size is growing. For example, let's say you have condensation on an aerosol. So as the condensation process goes on, the aerosol particle size, or actually the droplet size, increases. So this is an example of growth. Then you have birth rate. Birth rate means particles are, new particles are born, which means that you have, let's say, two particles collide, let's say two droplets collide, and because of that some fragmentation happened and new particles are generated. Or collision. So when we have a collision process, then also new particle is generated. But you have destruction rate also. Again collision. So a new particle is generated, but particles from two other sizes, let's say two small size particles interact to give rise to a large particle. Then for the large particle, the number has gone up, but for the small particles, the number has come down. So what does this mean? This means that you can write this equation for the number of particle sizes that you have. So we can have this equation written for the number of particle sizes that we are interested in. So I'm not going detail into how do we solve it or formulate it, but this is basically to give you an idea, overall idea. So, but usually the population balance equation is not solved directly. Rather, we integrate it with, rather we use moment based equation and then integrate that with the fluid flow equation. What does that mean? So, moment based equation means instead of working on the raw quantities, we take moment of that quantity. For example, this. So, if you consider the zeroth moment of the number density function, what do you get if you just integrate the number density function? What do you get? M0. It is nothing but the total number of particles per unit volume. Now, if you integrate this, that is dNddt, if you integrate this, you get this sum of all diameters. If you remember, this is how we defined different characteristic particle sizes when the number density function is prescribed. Then this is M2, this represents the total surface area. Similarly, M3, this represents the total volume. Okay, so like this, we can basically integrate this equation and get the equations in terms of different moments. So instead of solving the population balance equation for all particle sizes, you consider these moments and solve for, let's say, 3-4 moments. Okay. However, this itself is not a CFD model, rather it's a statistical balance equation that must be solved, that must be coupled to flow equations. How do you get the velocity? So where is the coupling coming into picture? Through this. So this is the particle velocity. How do you get the particle velocity? By solving the equations, the governing equations. But apart from that, you have to solve this also, if your interest is on resolving the polydispersity effect. Usually, this is coupled with Euler model, what we have just discussed. So finally, to summarize, these are the different modeling approaches. So basically, broadly, 3 approaches are present. One is fully resolved approach, then we have point particle approach, then we have population balance modeling. Now, each one we can consider from Eulerian and or Lagrangian framework. So, fully resolved approach, this is usually considered, you can say that it is similar to Eulerian Lagrangian. So, you are tracking individual particles, but you are solving the flow around each and every particle. Then we have point particle approach. Here we can have Eulerian Lagrangian approach, which can be DEM or DPM. We can have Eulerian, or this is two fluid model, and then you can have population balance modeling also. And here basically everything is summarized. Okay. So, in terms of how do they differ in terms of particle representation? So, this we have already discussed. Like in case of fully resolved, each and every particle is separately considered and the flow is resolved. In case of DEM, we consider finite sized rigid particle as far as collision is concerned. In case of DPM, we have point masses. In case of two fluid model, we have two interpenetrating fluids. And here basically we additionally solve the number density function. So, accordingly, so the accuracy, so basically if you see there is a trade-off between accuracy and the practical application. So, practically how much can you predict? So, in case of fully resolved flow, for example, in this case, the accuracy is the highest. Why? Why accuracy is highest here? Because we are not using any model. We are just solving the main governing equation. That is why it is the most accurate one. But apart from cost, cost is one factor. The other problem is the scale of the simulation. You can do this simulation, but in a very small domain. Okay, it is impossible to have the entire domain. For example, you cannot do a fully resolved simulation for, let's say, spray dryer. No, that's not possible. Within the spray dryer, some zone, region of the flow you can consider and then do a fully resolved simulation. Okay. So, finally, to summarize, the key takeaways are: you do fully resolved simulation when we need high accuracy, when we have least scalability, you cannot scale it. Then DEM, especially when we have contact dynamics in the play, which is used for dense granular solid fluid flows. We use DPM, which is much cheaper point particle tracking method. It is good for dilute flows. You need not restrict to sprays in dilute flows. Then two fluid model, which is macroscopic. It is scalable to industrial devices. But here we lose the particle level detail. You have no information about what happens to a individual particle along its trajectory. That is gone. In case of population balance modeling, this is an add-on equation that we have for the two fluid model, which is used to track particle distribution dynamics. Okay. So, so here we have discussed different modeling approaches in multiphase flows, but later we will see which numerical approach we need to follow, and that is mainly because of the turbulence present in the flows. So, even for single phase flows, we do not have a single numerical method to make the predictions. Okay. We have multiple methods. So, accordingly, because the single phase flow equations need to be solved in different ways depending on the degree of accuracy you need. Accordingly, the numerical methods for multiphase flows are also quite vast, and that is what we will discuss. So, in the next class, we will start first of all basics of turbulence and then see the numerical methods in turbulence, and then after that we will see numerical methods in the multiphase flows. Thank you.